Now let's look at geological time. If we look at the rate of geological processes, they're incredibly slow compared to the things we're normally familiar with. This is a diagram that shows many orders of magnitude of scale of rate of change. And on the right, we see things that are fast in our everyday world, like a car on a freeway, or a man running as fast as they can. In the middle, we have things that are still familiar, but essentially imperceptible. The rate at which grass grows, or your hair grows. Those are not visible to the naked eye. The geological timescales you can see are to the left, so they are orders of magnitudes, thousands or even millions of times slower. Now obviously occasionally Earth processes are fast, like earthquakes, certain seismic shifts, but most are incredibly slow. And geological time extends, therefore, and must be tracked over millions and billions of years. The fact that geological change is imperceptible to the human eye, or even sometimes over a human lifetime, is what made it hard, and it took a century or more for geology to emerge as a field of science in the 18th and 19th centuries. Here are some specific rates of geological change so you can get some real examples. The rate at which the Colorado River is cutting into the Grand Canyon is a rate of about 1 centimeter every 50 years. That's less than 1 millimeter each year. Obviously, you could return to the Grand Canyon after an entire lifetime and you barely notice 4 or 5 centimeters increased depth in the river. The uplift of the Alps, the opening of the Atlantic Basin, is similar. There are some faults that are difficult, that are harder to see, but easier to measure. The San Andreas Fault, for example, is quite a rapid rate of growth. The growth of the young volcano Mount St. Helens at 10 centimeters a year is also substantial. That's a meter in 10 years. And the deposition of Niagara dolomite is also quite fast. So there's a range in these geological rates, but they tend to be very slow on average. The founder of modern geology was a man called James Hutton, a countryman of mine, a fellow Scot. He was a farmer and a careful observer of the natural world who lived his life in the second half of the 18th century. He reasoned that the Earth was being slowly and continually formed and reformed by uplift, erosion, and sedimentation. And he worked out the first principles of how to measure the rate of change. Now, if you think about the gradual nature of geological change, it's a remarkable thing to be able to do. He was led to it by looking at places where people were building canals or railways at the beginning of the railway era, and he realized the strata of rock had probably been laid down over enormous periods of time. He had his particular realization in the formation you see here on the left at Sycamore Point, just outside Edinburgh, where there is old gray shale that's been uplifted, tilted, and eroded, then, in his mind, covered with an ocean, and the red sandstone subsequently deposited, only for it later to be raised up high enough to be on a cliff. So he's piecing together a chronology of this jumbled rock formation, and he's telling a story that plays out in time measured in tens or millions of years. His quote was, "The result of this physical inquiry is that we find no vestige of a beginning, no prospect of an end." There are some principles that underlie all of geology, right from the beginning of the field and even to the present day. The simplest and obvious one is the principle of superposition, that when you see a series of layers of rock and sedimentation or deposition is involved, the youngest layers are at the top and the oldest layers are at the bottom. And so we see the strata of rock and we can read age going downwards under our feet. There are also two kinds of ages in geology, and they're both relevant, and some are easier to get than others. There are relative ages, where we know the order of events, for example in the layers of deposition of a sedimentary rock, but not the actual dates. We know the Napoleonic Wars happened before World War II, and we know the bedrock in Scotland formed before the glaciers came in the last ice age. But we don't know their absolute dates without more information. With absolute dates, we know the dates, and we would know, for example, that the glaciers finally left Scotland about 11,000 years ago. In geology, we tend to need both forms of dating. We need relative dating to piece together the entire set of strata, but we also need absolute dating of at least some of the layers to piece together the chronology on a true timeline. There are two conceptions of Earth history, and Hutton and his colleagues strongly affirmed the second of these. One is catastrophism, the idea that great effects require great causes, and that to make the Earth the way it is, we need violent, catastrophic events. Volcanoes and earthquakes are examples of that, but this is imagining that the entire topography of the Earth is dominated by violent, sudden events. Hutton was well aware of the violence and sudden nature of a volcano or an earthquake, but he took a different view. It was called uniformitarianism. It was the assumption that we can use cause and effect to determine the causes of past events, but the general finding that Earth history overall is dominated by small-scale events, typical of what we see around us from day to day or year to year. And while catastrophes do happen, they are generally uncommon. There are principles of relative dating that still apply in geology. The law of superposition, where the oldest rocks are on the bottom, and then the principle of original horizontality, where layers of settlement are generally deposited in a horizontal direction. Rock layers that are flat have not yet been disturbed or deformed. But in many cases, for example in Sycamore Point, as we've just seen, there are angled rocks or rocks jutting out of other rocks. This is called cross-cutting, where younger features cut across older features. And the principle of cost-cutting relationships states that the geological feature which cuts another must be the younger of the two features. The layering of geology is very clear in a dramatic landscape like that of the Grand Canyon. Here we see on the left a photograph and on the right a schematic of the different rock types and formations, with the younger rocks being towards the top. Relative dating has principles that apply to it, such as inclusions, where a piece of rock that is enclosed within another rock, the rock containing the inclusion is therefore younger. Or what are called unconformities, where a break in the rock record is produced by erosion and sometimes by non-deposition of rock, and this typically will represent a period of geological time. Another important figure in this history was William Smith, working in England, a little after the time of Hutton. As many more canals and railways were built as part of the Industrial Revolution in the north of England where Smith lived, Smith and his friends noted the patterns of the strata and the fossils that were revealed by excavations. He also recognized the same patterns and even the same fossils contained in the rock at very different locations. He made a fundamental realization from the bank of the River Wear near Bath, which you see in the photograph in the lower left, where there's a dramatic transition between a lower layer that's rich in plants and an upper layer that's rich in seashells. And this same boundary is seen places that are 50 or 100 miles away. So he pieced together that a dramatic change in geology and biology had occurred about this time, presumably because there was an ocean and the seashell life forms were dead and deposited on the ocean, and underneath that was the older strata before the sea formed. William Smith spent heavily on what was a hobby, because this is still the era before professional science. He actually had to sell his fossils at some point, which was a very sad occasion for him, and he went to debtor's prison. But luckily, he lived long enough, and his fellow geologists and scientists gave him the acclaim he deserved late in his life. We can match up different areas, and this is a key part of how geology works, which is correlating the process of matching up rocks found in different places, finding the same age. It's done not only by the rock types, as you can see in the diagram, but also by the fossils that the rocks contain. And those are sometimes the best telltales or keys as to how to correlate a rock in one location from a rock in another location. We can get the relative ages of rocks using fossils, because the species that are laid down in fossilized form only have a certain span of existence, perhaps tens or hundreds of millions of years, and then they disappear from the fossil record, either below for older rocks or above for younger rocks. And so different fossils will give different ranges of measuring relative ages, and those relative ages should be intact at different formations in different parts of a country. The geological time scale was originally created based on fossils, and so it was a relative time scale. But since, in the last century, it's been quantified by radioactive isotope dating to give us absolute time. The structure of the geologic time scale names the eons as the largest divisions. There's the Phanerozoic, or visible life, the most recent eon that began in the Cambrian era about 540 million years ago. And then there's two earlier eras, which together are called the Precambrian, the Proterozoic and the Archean. Precambrian time, which is nearly 4 billion years, is almost 90% of the Earth's history. It's not divided into smaller time units because the events of Precambrian history are literally not known in great enough detail. We have very few rocks dating back to that time. The first fossil evidence of life in the rock record doesn't appear till the beginning of the Cambrian. We can only really fossil trace relative ages in the most recent 10%, or half billion years, of the Earth's history. Here's the geological timescale shown on the right, with the eons as the largest subdivisions, eras being the next subdivision, and the eras are subdivided into periods. So the Jurassic, for example, is part of the Mesozoic, and then the periods are divided even to smaller divisions called epochs. We now have a quite sophisticated version of the geological record, where we can clearly correlate the life forms present in the rock, what was happening geologically on the entire Earth, not just at one location, and piece together a chronology of our planet over 4 billion years. The Earth is a restless planet, and here we see an animation of the tectonic activity. The major discovery of the mid-20th century, after speculation by Alfred Wegener, was that the active interior of the Earth drives the slow but dramatic changes of plate tectonics. Here we see the last half billion years of the Earth, representing the moving plates of the Earth, the shifting of the continents and their migration into their current form. It looks dramatic in this speeded up version, but remember, this plays out over hundreds of millions of years. But these plate motions and tectonic activities have been directly measured. We can map plate motions down to the level of a millimeter or less per year across the size of a continent. So there's no question that tectonic activity continues to the present day. And that's the end of this topic.